Here we're going to introduce a very simple example of calculating the world's yearly income. It's a bit of a toy example, but we're going to imagine that we have a list of the incomes, the salaries of everybody in the entire world, and we're going to add them all up to work out what the total income of the world is. Now this is obviously a very simple example and slightly artificial, but we'll actually use it and come back to it in a number of contexts. First of all, it's very useful as a specific example of a real calculation where we can illustrate how much faster calculations have got through the increases, the developments in processor technology over the years. We talk about megahertz, gigahertz, and all kinds of things like this, but if we focus on a specific calculation, it'll maybe become more obvious what that actually translates into. Also, we'll come back to this example later on in the course to see how you might implement it in parallel. How would you use multiple CPU cores to do this calculation faster? So let's imagine we have a list. It's going to be a long list of the salaries of everybody in the world, ordered alphabetically by country and person. So right at the top of the list, we have a couple of people, Adel and Amir Abdali, who live in Afghanistan. Unfortunately, people in Afghanistan, the average wage is quite low, but they earn just under £1,000 a year each. We carry on down the list and we get a couple of representative people from the UK, Mark and Mary Henson, a couple who live in the north of England earning £20,000 or £30,000 each, and there's me, that's my salary. Oh, there seems to be a small error there. You can't quite see what my salary is, but anyway, I'm on the list as you'd expect. And way down at the bottom, we're assuming there are 7 billion people in the world, which is a reasonable estimate. A couple of brothers from Zimbabwe, Zoj and Zuke Zinyama, who run a successful garage and motor repair business, earning £3,500 and £1,000 each. So what are we going to do to add up all these numbers? But what we're going to do is going to write a computer program. Now, as I said before, this isn't a programming course. We don't expect you to be a computer programmer. However, this is very simple and it will serve to illustrate the way that the computers work and allow us to translate these megahertz and gigahertz frequencies we've been talking about into actual elapsed time in seconds. So how do we add it up? Well, first of all, we have a running total, which we set to 0, and we start at the top of the list. And we go through the numbers in order. So we add the income to the total. We go to the next item in the list, the second, the third, the fourth, the fifth. And then we repeat if we're not at the end of the list. So if we're not at the end of the list, but not at the 7 billionth entry, we have to go back, add the next income to the total, go to the next item, and then keep repeating. So we repeat these 3 steps, 3 individual steps, we repeat them 7 billion times. And once we finished at the end, we can print the total out. So it's a very simple prescription in some kind of pseudo language of the computer program to add up these incomes. But the most important point is that the core loop, the one that's executed 7 billion times, has 3 distinct steps in it. And we're going to assume that each one of these corresponds to a single instruction issued by the CPU, by the processor. Now that's quite a naive assumption, but it's perfectly okay for our purposes here. So the question is, how long does this calculation take? So what I'm going to do is I'm going to do a bit of history. I'm going to look at the history of processors over about the past 5 decades to see how long it would have taken to do this calculation on a particular processor from that time. And I'm going to focus on Intel as a manufacturer. Now, Intel is a very successful manufacturer today of processors. They're very prevalent in desktops and laptops. But there are other designers or manufacturers of processors you may have heard of. ARM, for example, who design a lot of the processors which go into mobile devices like mobile phones. NVIDIA, who produce graphics processors. There's also IBM, International Business Machines, who actually design their own processors, and AMD, who also make their own processors. But I'm going to look at Intel. Not only the main reason is because they have a long history, and we can look way back many decades to see how these things have gone on. Now, starting in 1966, which might seem like a strange starting point, but that's when I was born. So there I am in 1966. How long does it take me to do this calculation? Now, I have 100 billion neurons, which is a lot of neurons in my brain, but unfortunately, these neurons aren't particularly good at doing mechanical floating point operations. So I reckon I could issue an operations at the rate of 1 hertz. So that's the frequency 1 hertz, which is 1 operation per second, or 1 second per operation. Now remember, the core loop had 3 steps in it, so 1 operation per second, or 1 second per operation, it's going to take me 3 seconds to do that loop. And it turns out it would take me 650 years to add up the salaries of all 7 billion people in the world. And that's really, for one person, it's just not going to even complete in a lifetime. So it's a completely untenable calculation. Now back in 1971, Intel introduced what is now considered to be the first sort of modern integrated microprocessor, the Intel 4004, and it had 2,000 transistors. Not many transistors compared to my 100 billion neurons, but these transistors are very good at doing floating point calculations. The frequency of this machine was about 100 kilohertz. 100 kilohertz is 100,000 operations per second, or one operation every 10 microseconds. A microsecond is a millionth of a second. So every millionth of a second, this chip could do one operation. Now remember, there are 3 steps, so it's going to take 30 microseconds to do each loop. So the total time to do that 7 billion times is 2.5 days. So even over 4 decades ago, microprocessors were able to translate what would have been a completely unfeasible calculation for one person to do into something which could be done in a few days, which is a major step forward. But if we fast forward another 2 decades, we see the impact of Moore's law. Moore's law is this exponential increase, this regular doubling of the number of transistors you can get on a microprocessor. And in 1993, Intel released the Pentium, and in the intervening decades, the number of the manufacturing technology had increased to such an extent that they could now put 3 million transistors on the Pentium. That translates, this extra density of transistors translates into the ability to run these at a faster frequency. The Pentium had a frequency of 60 megahertz. That's 60 million operations per second. Or the time per operation is 17 nanoseconds, where a nanosecond is a billionth of a second. Now it's worth thinking about that for a while. A nanosecond is an extremely short period of time. Let's imagine a ray of light. Light is the fastest thing that there can be in the universe. And every nanosecond, light only travels about 30 centimeters. So each time that the Pentium issues an operation, it issues an operation every 17 nanoseconds. In those 17 nanoseconds, light has only traveled about 5 meters, about the width of a room. Now, it takes 3 steps per loop, so the time per loop is 50 nanoseconds, which means in 1993 it would have taken 6 minutes to add up the salaries of everybody in the whole world. So you can see in a couple of decades, a calculation which would have taken several days has gone into something which you could just set the computer going and go off and have a cup of coffee and come back and it'll be finished. So let's fast forward to 2012, another 2 decades, and Intel then released the Core i7 processor, which had 3 billion transistors, not 3 million, but 3 billion. It could operate at a frequency of 3 gigahertz, which is 3 billion operations per second. The time per operation is a third of a nanosecond. So each time that the Core i7 could issue an operation, every third of a nanosecond, light could only travel 10 centimeters. So you can see we're approaching some fairly fundamental physical limits here in how fast processors can go. The time per loop was 1 nanosecond. That meant that to add up all 7 billion salaries would have taken 7 seconds. So again, in the intervening 2 decades, from 1993 to 2012, we've gone from a calculation where you'd have to go away and wait to have a cup of coffee for it to finish to something you could just sit and it would be ready almost instantaneously. So hopefully that illustrates the impact of Moore's law, how from 1971 to 2012, over the period of 4 decades, this relentless increase in the speed of CPUs has gone from a calculation taking 2.5 days to taking 7 seconds.